I understand that you are 350.org and that you don't need to be convinced about climate change. However, I'm going to kind of take you through what I call the 3 S's of climate change anyway, and I'll try to kind of finish up quickly and then we can just have a conversation afterwards. I was specifically asked to touch on the IPCC Special Report about 1.5 degrees, so I have a set of slides in the middle about that. But simple, serious, and solvable. Oh, by the way, all of the slides are available at simpleserioussolvable.org. So if you want the slides, you're more than welcome to have the slides.
What more S? Sinful.
Sinful, that's an interesting S. There are lots of things that start with the letter S that go with climate change, and I invite you to think of your own S's. It's important to talk about how serious this is, but I like to sandwich the seriousness between what I call simple, which is odd for me to say that because I've been working on this for like 30 years, and if it's so simple, how come we haven't figured it out yet? But I always try to get to solvable because I think it's very important that we engage the solutions, that we don't just wallow in our despair at how serious it is. It's really important that we bridge into solutions, so we will. So start with simple. Do you ever wonder why day is warmer than night? Do you ever wonder why summer is warmer than winter, or why Phoenix is warmer than Fargo? It turns out that the answer to these 3 questions is the same answer. It's because when you add heat to things, they warm up. Okay? Day is warmer than night because the sun beats down on the ground and it adds heat to the ground and it warms up. And this is not mysterious. It's not something that, a lot of times people will tell me, oh, climate is so complex. Surely you can't predict the climate. Well, bullshit. I mean, we know that it's going to be warmer in Denver 6 months from now than it is now, right? And we know that for sure. And it's because adding heat to things warms things up. Heat can come in and heat can go out. And when we think about day-to-day weather changes, that's really all about heat coming in and out the sides, okay? Like the warm air that's here can be gone tomorrow, as you well know, and can be replaced by cold air that blows in from someplace else. That's weather. But when you look at the whole world, there are no sides. The world is round, and no matter how much sideways motion of the heat you get that's associated with the weather, it doesn't change the total amount of heat of the planet. The Earth can only change its total amount of heat through the top. And by the top, you're not used to thinking of the Earth as having a top, but it does. It has the top of the air, the top of the atmosphere. All of the heat that's exchanged between the Earth and the rest of the universe has to go through the top of the atmosphere. Now everybody knows where the heat comes from. It's at the top of the atmosphere. It comes from the sun. But if that was the whole story, that's just heat in, right? Heat in minus heat out equals change of heat. So if it's all heat in, the Earth's just going to get hotter and hotter and hotter forever until it like melts and boils and vaporizes, terrible things. So there's got to be heat going out, and there is. The difference between the outgoing heat and the incoming heat, these arrows through the top, is that the outgoing heat is invisible. You can see the heat, the sunshine coming in, but the outgoing heat is in longer waves than your eyes can see. It's infrared radiation. It's the same stuff. It's electromagnetic waves, but the waves are too long to tickle the little retina at the back of your eyeball, and you can't see the stuff, but it's there. I can feel heat coming off of this thing. Anybody's ever used an electric stove in the kitchen, before you can see the light coming out of those burners, you can feel the heat radiating out of those burners. That's infrared radiation, and the Earth radiates infrared heat out to space. So if more heat comes in than goes out, it warms up, and if more heat goes out than comes in, it cools off. It's really pretty straightforward. Now, the part that is a little bit more complicated is that the outgoing heat has to go through the air. The air is made of molecules. You can't see molecules either, but they're there. These 2 kinds of molecules, O2 and N2, 99% of the molecules in the air are just these 2 kinds. O2 you know about. If you didn't have it, you'd miss it. The nitrogen is basically fill gas. goes in, goes out, doesn't really do much. That's about 80% of the air. But both of these molecules, these O2 and N2 molecules, are diatomic molecules, two atoms of the same element, glommed together with shared electrons back and forth. Somewhere you learned this in like high school, that protons, neutrons, and electrons, the protons and neutrons in the middle, the electrons are on the outside. Those lines there are supposed to be shared electrons. The electrons are going back and forth. That's a chemical bond. Along comes this electromagnetic wave, right? Infrared radiations, electric fields and magnetic fields oscillating through space, fundamental property of the universe. Magnetic fields encounter this cloud of shared electrons in between the two atoms of, let's say, oxygen, and it can accelerate the electrons back and forth. Charged particle in a magnetic field, woo, 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 woo. Doesn't really make that noise. I just make that part up. But you can think of that woo molecule as being excited. We anthropomorphize molecules in physics. And these molecules that are excited have converted that electromagnetic energy into vibrational energy of the molecule. And then they can de-excite by sending that energy back out as a photon, up, down, sideways, whatever. And that's how molecules exchange energy with electromagnetic radiation. It's called spectroscopy. Now, because 99% of the molecules in the air are diatomic, that is the only interaction they can do with radiation. They can get longer and shorter, right? I mean, you look at those molecules, the only way you can rearrange that molecule is make it go like this. Woo, whoa, 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 back to its ground state. There's a tiny, tiny number of molecules in the air that are not O2 and N2. And by far the most abundant molecules in the air that have 3 atoms are these two. Oh, you can't see it very well. That top one is carbon dioxide, that's what we're here to talk about. CO2. Bottom one is water. And CO2 and O2 and H2O can absorb radiation too. And I only got the 2 hands, so let's just be carbon, okay? Oxygen, oxygen. Now a CO2 molecule. Along comes a photon of infrared energy, and I can absorb that and go woo, or de-excite, release that energy, go whoa, 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 back to my ground state. But there's more. Because unlike O2 and N2, it can go weep, boom, weep, boom, beep, boom, beep, boom, whip, whip. Each one of these different ways of wiggling that molecule will absorb a slightly different wavelength of infrared light, a slightly different energy level of photon. And that's what makes CO2 a greenhouse gas. It's not greed or capitalism or Al Gore. It's just geometry. It's the fact that there's 3 atoms instead of 2 atoms. There's more ways you can rearrange the geometry of a 3-atom molecule than a 2-atom molecule, and that's what makes CO2. Now, water vapor is even better because it's got that bend in it, can kind of do this thing, and this thing, this thing. Don't get me started about methane. But the molecules literally absorb photons and release photons based on their vibrational states, their geometry, and this is why CO2 is a greenhouse gas. So you guys have seen the cartoon before. The sun beats down on the earth. Much of it reflects off. The part that doesn't reflect off gets absorbed. That's what warms the earth up. All of that heat's got to be released back to space. The red arrows are supposed to be the outgoing energy coming from the earth. It gets trapped in the atmosphere by these bee-boo molecules and then re-radiated. Some of it goes up, but some of it comes back down. Now, I have in my office a radiation measuring device. And if I were to, shine it here on the audience, we would see what you all look like in the infrared. You're glowing. You're radiant beings, are we? This is like Yoda. But if I take that same instrument and point it up outdoors at night, there's no sunshine, but I'm still going to measure 300 and some odd watts of infrared heat coming down from the warm sky. Now, where is that coming from? It's coming from these molecules that are doing their little dance up in the sky. And it's like little tiny heat lamps in space, not in space, but in the air, shining heat down on us. Now, half the world has the sun, and the other half doesn't have the sun all the time. We call the half that doesn't have the sun night. And the night sky shines. There's actually more energy received by from the warm air than comes directly from the sun, because the sun's only on the day side, but the atmosphere is everywhere. So we actually get almost twice as much heat at the surface from the warm sky, from these radiating molecules, as we do from the sun. without this, the world would not be habitable. We could not have life on Earth. The oceans would be frozen to the bottom and be like, moons of Jupiter or something with the ice ocean. It brings me to what I call the common sense explanation of climate change. Many of you are old enough to remember what those things are. They're incandescent light bulbs. That's a 4-watt incandescent light bulb. Back when I was a kid, they were Christmas tree lights, and then when, my kids were little, they were night lights. So you plugged them in the hallway and they could find the bathroom. You guys remember these things? So, believe it or not, if you double the amount of CO2 in the atmosphere, these little wiggly molecules, it would add this much extra heat, 4 watts, to every square meter of the world. So, this table's about a square meter, give or take. Imagine a night light bulb there, and there, and there, and there, and there, and there, and there. But not just this room, and not just Colorado, but the entire world, covered with little 4-watt light bulbs every 3 feet. Now, if you did that, that would make the world warmer, because adding heat to things causes them to change their temperature. And that's basically the nut. That's how climate change works, is that CO2 molecules emit heat. Heat warms things up. 4 watts per square meter is actually quite a lot of heat. It's not that much. It's 4 watts. If they were 100-watt light bulbs, it'd be a lot worse. But every doubling of CO2 adds 4 watts to every square meter of the world. And believe it or not, all that was known before light bulbs were invented. It was discovered by this guy, John Tyndall, in 1863, when Abraham Lincoln was president. This guy put CO2 in a tube and measured the absorption of infrared light by CO2 gas in a tube. He did a bunch of other gases too, and he measured all different absorption at different concentration levels, and he wrote a famous paper 150 years ago explaining that if we burned a whole boatload of coal, more than one boat, it would add enough CO2 to the air to change the climate. So this is not something that we've discovered recently. This is something that science has understood for centuries, for a very long time. Brings me to what I call common myth number 1. Very, very widely held myth is that scientists figured this out when it got hot, right? So the myth is scientists expect it to get warmer in the future because it's been warming up lately. And of course it has been warming up lately, right? Everybody's seen these graphs where it used to be cooler and then it got hotter and then it got hotter faster. And that's true, but amazingly, we knew this was going to happen 150 years ago. This is not something that we saw it getting hot. Gee, I wonder why it's getting so hot. And then correlated against CO2 and figured out maybe it has something to do with the CO2. No, that's just not true. Actually, the reason why we know that adding CO2 to the atmosphere will warm the climate is because we know that when you add heat to things, they change their temperature. This is formally called the First Law of Thermodynamics, but you got to be some sort of egotistical Victorian Brit to call something that simple the First Law of Thermodynamics. For God's sakes, cavemen knew this. They put the mammoth on the fire and it got hot. But they didn't say First Law of Thermodynamics, they said ugh, hot. So, the law of ugh, hot shows that when you add CO2 to the air, you get a warmer planet. It's really that simple. So I agree, I understand it's complicated. I'm a professor, I do this stuff all the time. I've been doing it for decades, since I was young. But the basic story of how it works is simple enough that really anyone can understand. And I hope that this wasn't just a waste of your time to hear me kind of explain how it works. Now, we got, question?
Will you sort of explain the difference between the sun's radiation and infrared that's reflecting back, and why only the infrared heats the molecules in the same way?
Great question. So the sort of big expensive word for that is selective transparency. Okay, the gas is selectively transparent. We know that visible light is passed through air, or I couldn't see you, right? I can see through air. Visible light has short waves. Here's a meter. If I hadn't had coffee this morning, I could maybe make a millimeter. It's 1,000th of a meter. And 1,000th of that is a micron. And visible light's about a half of that. So half of 1,000th of a millimeter, the waves, right through the air like nothing. infrared heat from the Earth is about 20 times that long of a wave, and it's just the right frequency to wiggle these bonds in the gas. So the gas is opaque to the infrared because the waves are just the right frequency to wiggle those chemical bonds in the molecule, but it's not the right frequency to absorb visible light, or it would just be dark. Good question. So now we got to talk about how serious it is. And you know, you're 350.org. You know that this is serious. But we have to talk about it because it is. It's a problem whose seriousness gets worse and worse and worse until you stop making it get worse. And then it doesn't get better. So it's bad-ish now. It can get much worse. It can get way worse than that. It can get way worse than that. It will become the biggest problem there is unless we solve it. So we must solve it. How much warmer are we talking about? It depends. These are maps of how much warmer we expect it to get in the 21st century. Low emissions, medium emissions, high emissions. Obviously, the more carbon you burn, the hotter it gets. But that's not all, because you notice that the maps are not all the same color. The different colors are different amounts of warming. First thing you might notice is that the oceans don't warm up as much as the land. And that actually makes a ton of sense. Remember the 4-watt light bulb? You guys know how deep the oceans are? Really deep. Really deep. On the average, about 13,000 feet deep. Imagine a 4-watt light bulb on top of 13,000 feet of water. How much temperature change are you going to get in 13,000 feet of water with a 4-watt light bulb? Not very much. So the oceans warm up slowly because you got this tremendous mass of water to drag the temperature around. The next thing you might notice is that the southern hemisphere doesn't warm up as much as the northern hemisphere. And that's because the southern hemisphere is mostly ocean and the northern hemisphere is mostly land. And then the third thing, if you look more carefully, you see that the Arctic warms up way more than any place else, and that's because the Arctic is currently snow and ice. And if you warm up the Arctic enough to melt the snow and ice, then you can soak up all this extra sunshine up there. It's not reflecting off the snow and ice. That adds to the 4 watts you get from the CO2. Now you also got extra sunshine that you're absorbing. So if you happen to live on land in the northern hemisphere where it snows, you get extra. You don't get global warming. You get about global warming and a half. A little more than that, actually. So you know anybody who lives on land in the northern hemisphere where it snows? Oh, yeah. All of us. You know, that middle of North America right there where we live, in the low emissions world is about 3 degrees of warming. In the high emissions world, it's about 6 degrees of warming. Oh, but wait, those are Celsius degrees. So to convert Celsius degrees to Fahrenheit degrees that the rest of you use all the time, you multiply by 1.8. It's about almost 2. So instead of 3 degrees to 6 degrees of warming, you get more like 5 to 10 degrees Fahrenheit of warming. Now, even that doesn't sound too bad. I don't know, what was it, like 45 today? So 10 extra degrees would be 55, and I probably would have been okay with that. But we're not talking about just today. We're talking about on the average 10 degrees. Now, nobody probably here, except maybe Chuck, knows what the average temperature is in Denver. No. Well, maybe you do. I don't know, and I'm a meteorologist. So I have put up a helpful map here that shows the average high temperatures in the United States in Fahrenheit, the degrees that we're used to. And each color on the map is 5 degrees Fahrenheit warmer on the average than the color next to it. And I got a dot for Denver there and some other dots. And I'm going to move the dots 2 colors on the map, which is 10 degrees average warming. And holy mackerel, 10 degrees of warming is like moving to freaking Albuquerque. 10 degrees warming is a lot. If you were a farmer in eastern Colorado and they swapped out the climate of Albuquerque for, Lyman, they would totally notice that, right? That would be a big deal. Illinois turns into Mississippi. Washington, D.C. turns into Tallahassee. Oh my gosh, 10 degrees Fahrenheit of average warming is like moving 600 or 800 miles south. It's a lot. Now around here, We don't have to move north and south to find a place with different temperatures. Where do we go if we want to find a colder place around here?
Mountains.
The mountains. Our mountains have all these different zones. You guys have seen pictures like this before. Turns out about every 3,000 vertical feet is about 10 degrees Fahrenheit in the average temperature. So 10 degrees of warming swaps out the temperature of Denver for the temperature of Estes Park, or the temperature of Estes Park for the temperature of Trail Ridge Road. Now, at the end of the last ice age, we had about 10 degrees Fahrenheit of warming, and the zones all marched up. Now, you don't remember that. That's okay. But it was about 18,000 years ago to 8,000 years ago, there was warming across the whole world, really. But in our part of the world, the zones all moved up the mountains about 3,000 feet, 10 degrees Fahrenheit. But it took 100 centuries for that to happen. And in 100 centuries, you got plenty of time for trees to spread seed that, spreads the trees grow and then more seed. And so the trees, it's not like in Lord of the Rings where the trees just walk up the mountain. They actually have to die and grow new generations of trees. And it takes freaking centuries for that stuff to happen. 100 centuries. We're talking about that much warming in 1 century. 1 century is not enough time for the trees to march up the mountain. It's not enough time for the different vegetation zones to keep up because they don't walk. They have to grow whole generations of trees before they can move. We happen to live in an area of the world that's very vulnerable to climate change. Now, we're not unique in that. Almost everywhere is very vulnerable to climate change. It's just that for us, it's the water. Okay, so this is a map of the western U.S. It's the average precipitation, annual precipitation in the western U.S. And I don't know, if you ever drive to California, you know that it's mostly brown out there, and it's just like that, mostly brown on this map. The average precipitation here is about 14, 15 inches, 16 inches a year. We have 5.5 million people in Colorado living on 15 inches of water. In that map, total about 75 million people live on that map. Actually live in the parts of the world that are represented by that map. How do we get away with that? We get away with that because of the blue places. You know what the blue places are called? Mountains. The mountains reach way the heck up in the sky and they convert the water vapor as it goes by into snowpack. And snowpack is our water supply. Something like 80% of our water supply, not just here in the Front Range, but in the western U.S. as a whole, comes from melted snow. The mountains are the water towers of the West. The amount of water that is stored in our annual snowpack dwarfs the amount of water that we can store in our constructed reservoirs. This is our major water supply. And if you swapped out the climate of Albuquerque for the climate of Denver, you'd have less snow. That's our water. We would miss it. We would big time miss it. This is 50 years worth of snowpack data for Colorado, and you can see the bouncing around, right? Every year is different. We're having kind of a snow drought right now, but we had good snow a month ago. 2011, we had epic snow. 2012, we had pathetic snow. But if I ran a best fit line through 50 years of data, I see about 20% less snowpack on the average statewide in Colorado than there was 50 years ago.
Where's that data set from?
This is from the USDA Soil Conservation Service. Statewide snowpack, 50 years worth of statewide snowpack. That's with less than 2 degrees Fahrenheit of warming. We've lost 20% of our snowpack on the average in 50 years. Now, I just told you 10 more degrees of warming. You do the math, right? What does that mean for snow? Bill Ritter, our former governor, told me, Scott, Colorado will be the last best place for snow in the United States, for skiing is what he meant, because we have the highest mountains. California, Oregon, Vermont, Adirondacks, all those places are going to lose their snow decades before our highest mountains here, and therefore everybody will want to come here to ski because they won't be able to ski anywhere else. It's not just about water supply, though. It's about water demand. In fact, it's even more about water demand than it is about water supply. when the air is hotter, it evaporates more water. If you don't believe me, try it, at home with a couple of pans of water, put one on the stove and one not on the stove, and see which one evaporates faster. Everybody who's ever watered the lawn or had to take care of a garden, you know that on hot days you're using more water than you are on cool days. And so 10 degrees Fahrenheit of warming dramatically increases the evaporative demand of the air, which therefore means you got to have more water. And that's true whether you're watering your lawn, or you're trying to supply water to a city, or God help you, you're trying to grow crops, or take care of a forest. All of those systems use more water when it's hot. So it's not good enough to just maintain the water we have. If we're going to make it 10 degrees warmer here, we need way more water. Oh, but we're also going to try to bring in 60% more people. What the heck? Something's got to give. Another thing about our particular situation is that a warmer climate promotes wildfire. And there's three fundamental reasons. The first one I already just mentioned: warmer air evaporates more water, so you have more evaporative demand. Each day in the summer, if it's 10 degrees hotter, you're going to evaporate more water out of the forests. Now, think about it for a second. Our forests up in the mountains get this huge slug of water in the spring, right? When the snow melts, it comes down and it waters the heck out of the forest. They call it mud season. And then the soils are saturated, and then all summer long, you use that water. The trees are sucking water out of the root zone and evaporating it through the needles and putting it out in the air. And if you take more out every day all summer, you're going to run out by the end of the summer. And that's like that crunchy time of the year in August, September, when you walk in the forest and the litter is all crumbly under your feet. Not only that, in a hotter climate, the warm season expands. There's more months of hot season. There's more months of fire season is what we're getting to here, right? Instead of just having, say, June, July, and August to get through on your limited amount of water, you may have from May to October, or even April to November to get through. And so you not only do you use more water every day, but there's more days of water use in the forest. And the third thing is, those really bad, hot, windy days when it's like 99 degrees in the shade and 3% relative humidity and it's windy and the fire jumps over the highway or the river and it burns subdivisions and they have to evacuate all the firefighters? Those days happen way more often in hot climates than they do in cold climates. Those really bad days. So for all of those reasons, increasing the temperature increases the amount of wildfire. We've had about a doubling of acreage burned every summer in the western U.S. in the last 30 years, but you ain't seen nothing yet. Another degree of Celsius of warming in our region, I don't know if you can see these numbers, probably not. This is Colorado, and they expect something like 650% increase in wildfire in our mountains per degree Celsius of warming. So if you're talking about 2 or 3 or 4 or 5 degrees of warming, oh my gosh! It gets to the point where the return time of the fire is shorter than the time it takes to grow trees. And at that point, there's no more forest. Only you haven't replaced the forest with equilibrium vegetation that would have replaced that forest if you gave it 100 centuries to do so. You replace it with cheatgrass or, yucca or, prickly pear, something that can grow quick in a fire scar, because everything becomes fire scars. It's a terrible story. You don't want to do this. All right, now you asked me specifically to talk about this report. The IPCC is Intergovernmental Panel on Climate Change, comes out with periodic reports. And in 2015, the nations of the world agreed in Paris to limit warming to well below 2 degrees Celsius above pre-industrial conditions. But they also put some text in that agreement that said preferably below 1.5 degrees above pre-industrial. And so the governments of the world asked IPCC to do a special report, SR15, SR15 for 1.5 degrees C, where they said, first of all, what's the difference? If we keep warming at 1.5 degrees versus 2 degrees Celsius, what's the difference? Is it really that big of a deal to keep it at 1.5 versus 2? And secondly, what would that take? How hard would it be to limit warming to 1.5 degrees instead of 2 degrees. So I have 3 slides on this report, and they're the 3 sort of main results out of the report. The first result is time is short. Okay, now Martin asked me to stand in this one place. I just can't do it. I'm going to go stand by the graph. You're going to have to figure it out. All right, so here's years, and here's temperatures, and you know, you are here. This is history. This is back to 1960, and here we are, 2017, 2018, whatever, 2019 now. Time flies. Temperature's obviously been going up. We are currently right about 1 degree Celsius above pre-industrial. Following that same warming trend that we've been on, we will cross 1.5 degrees Celsius in about 2040. Now, when this report came out, a lot of the news coverage said we have only 12 years left because it was 2018. Well, guess what? Now it's 2019. So 11 years till we cross that threshold, and 2C is somewhere in the future. So that's the first message out of this report, is that holy mackerel, 1.5 degrees C is like right around the corner. 1.5 degrees C is a decade away.
21 years away.
Oh, sorry, 21 years away. Yep.
Short.
All right, my bad. Can't do arithmetic. Message number 2. Dramatic cuts are required. So this is nothing new for this report, but let me just tell you, you probably already know this. This is why your organization is called 350. Really the only thing that matters about how high CO2 gets is how much total fossil fuel is ever burned. Okay? So it doesn't really matter how fast you burn it, you get to the same CO2. Because there's really nowhere else for it to go. You're shoveling it up in the air, and it's not like water that comes back down. It just stays up there. So these are global CO2 emissions in billions of tons of CO2 per year. You are here. 2040 is here. Looking at something like an 80% emissions cut by 2040 in order to meet that 1.5 degree target. Something like 100% by 2050. And let's face it, as I told you, the only thing that really matters in the long run is the total amount of fossil fuels ever burned, ever in the history of the planet. So it's got to go to 0. It has to go all the way to 0 and stay there forever. Yes?
Quick question for you. The plants
Yes.
do absorb CO2, as well as phytoplankton in the ocean that
Right.
absorb CO2. So there is sequestration that.
Then they
that
die.
happens. They die.
Well, the dying is a very important part of this. So since you asked, plants and photosynthesis in general suck out 1/7 of all the CO2 in the atmosphere every single year. So in 7 years, there's no CO2 and it's the end of the world. Wait a minute. There's something missing there. And the thing that's missing is death. Okay? Life and death have been in almost perfect balance for most of the history of life on Earth. For more than 1,000 years before the Industrial Revolution, the CO2 was amazingly steady. We know that because we have the actual air. That means that even though 1/7 of all the CO2 is scrubbed out of the air every year by plants, 1/7 of it is created every year by microbes that decompose those plants. So having photosynthesis does not suck CO2 out of the air on the net. The only way you get CO2 sucked out of the air on the net is if plants are growing faster than they're dying. And in fact, that is the case. Plants are growing faster than they're dying, but only to the tune of about 1/400th of the CO2, not 1/7 of the CO2. So it's a tiny, tiny residual between growth and death. Good question. All right, returning to this, 80% cuts by 2040, 100% cut by 2050. If you miss, this big blue area happens, and that's emissions below 0. And it doesn't take much of a miss. You follow this gray path instead of this blue path, and you wind up having to go very strongly negative to the tune of about 1/4 of our current fossil fuel emissions. So if you think it's hard to get from here to 0 by 2040, wait till you see how hard it is to suck out 1/4 as much CO2 as we currently burn by 2060 or 2070. Oh my God. It is technically feasible, but here's the deal. We break carbon molecules and create CO2 because it's fun, right? Because energy comes out when you do that. Grabbing CO2 molecules out of the air and gathering them up and sticking them in the ground, that uses energy. It doesn't create energy, it requires energy. Where are you going to get the energy to suck out that much CO2 out of the air every year? Oh, we could burn a bunch of coal. No, that is a losing proposition. In order to get to that negative emissions thing, you've got to have an abundant source of carbon-free energy. And if you have an abundant source of carbon-free energy, why not use it to power the world, right? This is child's play compared to this. The cutting of emissions 80 or 100% in the next generation is much easier than sucking out massive amounts of carbon every year for the rest of your children's lives. So it's much, much easier to do the cuts as quick as we can than it is to fail and then have to go chase after the CO2 after it's diffused, dilute out into the air. Third big thing out of that report, it's worth it. It's totally a different story at 1.5 degrees than 2 degrees. Now, sorry, complicated graphs. You ever notice that about IPCC reports? They're almost unreadable. I don't know if you can even see this. There's a whole bunch of different impacts here. Warm water coral, the Arctic, terrestrial ecosystems, coastal flooding, rivers. Here's where we are now at 1C. The colors indicate bad, okay? Like white is not bad, and yellow is getting there, and red is bad, and purple is forget about it. Bummer for the corals already, right? Here's 1.5 degrees, and here's 2 degrees. And for a lot of these things, it gets way worse at 2 degrees. Like, look at the Arctic at 2 degrees versus 1.5 degrees. Look at terrestrial ecosystems at 2 degrees versus 1.5 degrees. Big differences at 2 degrees versus 1 degree. So my takeaway from this report is that as hard as it is and as soon as it is, it's worth doing 1.5 if you can, because it makes a big difference. Now, I'm sorry, I remember now where I got the 12 years, which was wrong. The 12 years is how long we have to start really bending that curve down, the emissions curve, in order to achieve the 80% reduction by 2040 or the 100% reduction by 2050. So you will often hear this entire report summarized with 3 words, 12 years left. Have you heard that phrase? Almost everybody's heard that phrase. Now, I got another 3-word phrase for you, no giving up. Okay? So here's the deal. It's not binary. It's not like up to 1.49 everything's fine, and then at 1.51 everything's fucked. It's not like that. It's not a binary choice. It's a continuum. 1.5 is worse than 1. 2 is worse than 1.5. 3 is worse than 2. 5 is way worse than 3. In fact, the impacts become exponential. So every extra degree is much worse than the degree that came before. So the other thing, which I didn't really get a chance to talk about here, is it takes for freaking ever to get rid of the CO2. Now, you've mentioned photosynthesis. Actually, the biggest way that CO2 will go away in the long run is to dissolve in the oceans, thereby acidifying the oceans, and that's another whole terrible thing that we could talk about. But the oceans are stratified. The warm water floats on the cold water. It takes energy to mix the warm water down. The only place in the world that the ocean surface water can mix to depth is at the poles in the winter. So think, January in Greenland and July in Antarctica. 1/1000th of the ocean sinks every year by that mechanism. So it takes 1,000 years to turn over the ocean once, 1,000 years to turn it over again, 1,000 years. So roughly 3,000 years from the time we stop burning fossil fuel, the CO2 in the atmosphere and the ocean will come into chemical equilibrium. 3,000 years is a long time. 3,000 years is half the time since the origin of writing. So this is a problem for millennia. And in fact, even when the CO2 comes into equilibrium with the deep oceans, it's still tens of thousands of years to get rid of the last 20% of it. So what we're talking about is if we fail in this generation, the next generation, it's not just the 7 billion people on Earth, it's hundreds of billions of people over millennia that will be miserable because of our failure. We mustn't do that, okay? But we must resist the temptation to say 12 years or we're done. I don't know if you guys read Dave Roberts. You guys know who he is? He writes for Vox. His Twitter handle is drvox, like Dr. Vox. He wrote this great article last week called The Case for Conditional Optimism on Climate Change. I quote from him here: "There is no such thing as game over, or too late, or screwed, or no hope. No matter how hot it gets, the stakes will always be enormous. Time will always be short. There will never be an excuse to stop fighting. You have to keep it up. Even if it gets to 1.5, even if it gets to 4, you gotta keep it up." It's not helpful to say, "Oh, screw it, we're done." We can't do that. It's a moral hazard. It's a slippery slope. Don't go there. All right, so I got to talk about solutions because it can be solved. Okay, the solutions are there. The solutions are available to us. We can do this. I'm going to show you one more math thing. I know people aren't into math. How much will we burn? This guy, Japanese economist, his name is Kaya. Is Kaya dead? Don't know. Chuck knows more about this stuff than I, so I ask him about it sometimes. All right, so this is an equation, sorry, but it's easy, okay? The CO2 that we emit is equal to 4 things multiplied by each other, okay? Population times wealth per person. It's not really wealth, it's economic, it's buying and selling per person, times the amount of energy it takes to make $1, times the amount of CO2 it takes to make energy. Okay, so this is called the Kaya identity, and the reason that mathematicians call something like this as an identity is because if you do the algebra, you can prove that it's exactly correct. Okay, so like the E cancels the E, the dollar cancels the dollar, the P cancels the P, and you just get CO2 equals CO2. See how that works? Yeah. So you got these 4 things. Everybody remembers the population bomb. I'll ask those of us of a certain age. This is world population since 1750. And look at that, exponential when we were kids, right? This is 1950. Here's when I was a kid. This is the first derivative of this curve. So the rate of population growth is the red and the world population is the blue. The rate of population growth is half what it was when I was a kid. The rate of population growth is half what it was when I was a kid. Amazing. The world population has doubled in my lifetime. It will never double again. We expect world population growth to reach 0 by the end of the century. It's remarkable. It's due to the demographic transition, right? People first start to get rich and they live longer, and then a generation later, their kids have fewer kids, so the birth rates go down. That's P. Remember, P times all this other stuff. I'm going to look at the next term next, which is money per person. These are 2 pictures of Shanghai. They're taken from the same spot. See the clock tower here in the foreground? These pictures were taken 20 years apart. This is not population growth you're seeing in Shanghai. This is economic growth that you're seeing in Shanghai. Shanghai has more people in the city limits than any other city on Earth. 22 million people in the city limits. And it's completely surrounded by suburbs that have more than 10 million people per town, and you've never heard of a single one of those suburbs. Shanghai metro area has 75 million people, as many people as west of Mississippi. Amazing. And Shanghai used to be dirt poor a generation ago, and it's not dirt poor anymore. I went there, I was stunned by the air pollution, but also by the affluence, by the people in fancy clothes and in nice restaurants and the bullet trains and it's a nice place. It's just like the freaking capital of the world. It's amazing. There's 7 billion people on Earth, but there's only 1 billion people like us. By people like us, I mean people who use a lot of energy. There's 6 billion people in the world who hardly use any energy compared to us. And the total amount of people like us is expected to reach 4 billion by the end of the century. Okay, so again, it's not population growth. Population growth is going away. It's economic growth. It's the fact that the number of people like us is exploding. And it's not because we're having lots of babies. It's because people who are dirt poor they're not as dirt poor as they used to be. So it's a good thing, right? You don't want people, you can't wish people to be desperately poor. But if they become middle class by burning coal, we are in a world of hurt because there's billions and billions of them. Population is only expected to grow 30% this century, but energy use is expected to increase 300%. 10 times the rate of population growth. Okay. I'm going to skip this. Nah. Yeah. Okay. I want to show you something that is good news. The International Energy Agency, IEA, every year does these projections of energy use out for decades. And they've been publishing these reports. This first one is from 2006. So here's how much new solar was projected out to 2025 by these guys back in 2006. This is their prediction that they made in 2008, 9, blah, 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 blah. You see what's happened? This is for the same kind of graph, but for wind. So every year, these guys, who are like world experts on energy markets, predict that the amount of new solar and new wind on the grid will be flat forever. What? The actual amount of new solar and wind are these dashed lines. And clearly what they've done is each year they just take the actual for that year and just project it out flat forever. It's amazing. It's because the prices of these technologies have fallen way, way faster than anybody expected. Solar panels, no longer the most expensive part of solar energy, PV panels have fallen in price by more than a factor of 200 since I was in high school. They have fallen in price 80% since 2011. It's amazing. Wind has similarly gone through these changes, and batteries are going through these changes. It's a different world. If you have factoids that you learned 3 or 4 years ago, they're wrong. They're just wrong. The prices of these technologies has fallen dramatically faster than was expected 5 or 10 years ago. So now I want to talk about costs. Oh yeah, I forgot to mention. I should go back to Kaya for a sec. If these are the 4 things that control CO2 emissions, and the product of these 4 numbers is the CO2 emitted, what did I say has to happen to the CO2 emitted? Has to be zero. It has to be zero in a generation. Well, we could kill all the people, but you can't, right? That would be wrong. You could eliminate the world economy. That would similarly be devastating to an awful lot of people, all of those people. So you really almost can't make these 2 go down. You certainly can't make them go down 90% in a generation. It's not possible, and it's arguably wrong. So these are the only 2 dials you get. These are the 2 you get. You've got to make money with less energy, and you've got to make energy without releasing CO2 in the air. It's just math, right? There's really no way around it. That's why I mentioned the solar panels. All right, sorry. Let's talk about costs. Yes, there's a toilet on here. I'm going to ask that you not use it yet. The conversion of the entire world economy from our current fossil fuel base to a non-carbon energy economy is estimated by economists at something like 1% of the global economy.
That's peanuts.
You're right. So, let me just tell you, first of all, it's not just some crackpot economist who comes up with this 1% number. Many economists, there's a whole field, climate economics and environmental economics. These guys come up with different estimates, and it's anywhere from 0.5% to 2%. Nobody in that field thinks it's 5 or 10% of the world economy. Everybody is in the low single digits to maybe less than 1%. Now, does anybody know what, besides Chuck, what the value of all the goods and services sold in a world in a year is? That's the global GDP. No guesses.
80 trillion.
Very, very good. $80 trillion, give or take. Almost dead on. $80 trillion a year times 1% is $800 billion a year. That's more than the US spends on defense. That is a lot of money. Yes, it's peanuts, but it's more than the US spends on defense. So we're talking a huge effort, right, to spend $800 billion a year to solve this problem. That's about what it cost my grandparents' generation to retrofit all the world's cities with indoor plumbing. 1% of the world economy. 100 years ago, people dug up every street in New York and London and Paris and Tokyo, and they laid sewer pipes. They knocked out tenement walls 20 stories high, and they put in hot and cold running water. They knocked out internal walls, and they put in sinks and toilets and showers, and boy, howdy, are we glad they did that. Not only do we not have to poop in the street, think what it did for plumbers. Think what it did for plumbing suppliers. Think what it did for the grocery store down the street from the plumber, or for the children of that plumber who could use that money to go to college. This is what people do. These are my grandparents. That's Max and that's Florence, long dead. It was their generation, not them personally, that did that indoor plumbing thing. And then when they were done spending 1% of the world economy on indoor plumbing, they spent another 1% of the world economy on rural electrification and fighting the Nazis and building subways. I mean, these people were the greatest generation, right? They did all this amazing stuff. And they did not crash the world economy doing that. They actually, their generation did crash the world economy, but it wasn't because of infrastructure spending. These are my parents, that's Margie and Bob, and their generation picked up the torch, and they went on and spent 1% of the world economy on interstate highways, and much more than 1% of the world economy on the Cold War. They sent people to the moon and back. Amazing, amazing people. We haven't been on the moon in 50 years, but it was my parents' generation that dug deep, and they did not crash the world economy, spending 1% of the world economy on highways and stuff. This is my wife and me back when I had hair. And our generation spent 1% of the world economy putting computers on every desk in every office of the world. And when we were done with that, we went on to replace billions and billions of landline phones with these $1,000 monstrosities that you use to watch YouTube videos. I still pay my children's data charges. So it didn't crash the world economy to build computers and the internet and cell phones any more than it's going to crash our children's economy to save the world. These are my kids. That's Matt and that's Nate, and they get to do it again. They get to replace usable infrastructure that isn't working for them with much better infrastructure that works better. Duh! It's what we do, man. It's what we've been doing for 500 years. Our culture has thrown away perfectly good technology like sailboats and replaced it with steamships, or perfectly good technology like, carriages and replaced it with cars. It's what makes modern life, right? This is normal. This is not out of the ordinary. It's not even a lot of money. Like Martin said, it's freaking peanuts. You get to choose your vision of how history works. A lot of people tell a story that actually hangs together pretty good as a narrative. The story is that our modern world is based on extraction. It's based on stuff we dig out of the ground. You can imagine a lump of coal, and there's value in that coal. And somebody sold that coal to somebody else for a profit, and they set it on fire. And they sold the energy for a profit. And somebody bought the energy and used it to make products and services, sold those for a profit, and you wheel and deal, pretty soon you got an $80 trillion a year global economy. And maybe that is how history works, but God, I hope not. Because if that's really the story, then when you stop burning coal, you go back to the Middle Ages. You go back to freezing in the dark, only there's billions and billions of you by then, and you're just screwed. It's a grim, terrible, tragic story. You do not want to tell that story to your kids. I like this story better. We built this world. Our world doesn't come out of extracted minerals. Our world comes from in here. It comes not from the ground, but from the sweat of our brows and the sparks in our souls. And we're not running short of those things. And the kids are going to be okay. Thanks. Is it just me or is it warm in here? Somebody maybe open a window, I don't know.
Thank you so much. Questions, everyone?
Or comments or whatever. Yeah.
Yeah, I've been interested lately, and I'm not super knowledgeable in it quite yet, but the concept of glacial rebound, and really wanting to understand really what that is and what its impact are on things like sea level rise or coastal flooding, and how it impacts climate change and vice versa, how climate change might impact.
So glacial rebound. Well, let me make sure I got the right.
Question?
Yeah, the question was, tell me about glacial rebound and how is that related to sea level rise and climate change?
Yeah, and vice versa.
And
how
vice
climate
versa.
change impacts glacial
Okay,
rebound.
18,000 years ago, which sounds like a really long time, is a long time, my perspective, but not so long ago that there weren't people running around, right? 18,000 years ago. A third of the land surface of the northern hemisphere was covered with ice, solid ice, mile thick, more than a mile thick. And the weight of that ice, this is the question you were asking.
Yep.
The weight of that ice literally depressed the rock underneath it and made like concave bulges underneath the ice sheets. And when that ice melted, it melted much more quickly than the rock could rebound. It took thousands of years for the rock to come back up. So when the ice first melted, the sea came pouring in. I went to college at the University of Maine, and the place where I went at the University of Maine is currently 60 miles inland. It was under 400 feet of ocean at the end of the last ice age because the weight of the ice had pushed it way down, and then the ocean came in after the ice melted, and it took thousands of years for the land to bounce back up once the weight was off. So glacial rebound is usually, we refer to it as the rebound of the rock, and sometimes it overshoots and then it kind of wah, wah, wah. Parts of Scandinavia are still doing this, for example, where the ice melted more recently. So sea levels go up and down locally due to many things, including land going up and down, not just the water going up and down. And glacial rebound is one of the biggest reasons why that happens. However, there's also global sea level, which is rising because of two fundamental things. One is the water is warmer and it expands. And secondly, there's more of it. There's more water because water from the ice sheets melts and goes into the oceans and adds volume to the oceans. So globally, the average sea level is going up. By the end of the century, anywhere from, let's say, 2 feet to 8 feet of extra water, global average. On the other hand, locally, you got land that goes up and down, on top of that. So for example, Louisiana is sinking like crazy. Louisiana is sinking because it used to be filled from the silt from the Mississippi River, the Mississippi Delta, and the weight of the silt pushes it down. But now there's no more silt coming from the river because it's all in levees and it gets squirted out in the Gulf of Mexico. So you've robbed that sinking land of the silt to fill it back in. It's sinking like crazy. Plus the water's coming up. Those people are in a world of hurt. And today it's Louisiana, tomorrow it's Florida, then it's Norfolk, Virginia, then it's New York City. And forget about Shanghai. I mean, my God, unbelievable numbers of people. So something like 600 million people. 600 million people are at risk of losing their homes for sea level rise in the 21st century. That's twice the population of the United States. Imagine you think there were a lot of refugees from Syria in Europe. Imagine 600 million of them, my God. So I don't know if I answered your question, but that's good.
Yeah, I guess maybe a follow-up question.
We got others too.
Would that, compared to the sea level rise that's caused by climate change versus that glacial rebound concept, certain regions may be more impacted by glacial rebound than actual sea rise. And I guess there's some climate skeptics who would say that glacial rebound is more responsible for submerging
some places that's almost certainly true. There's places where the land is going up and down faster than the sea is coming up for now, but globally that's not the case. Okay, somebody else.
Judy?
I've been very encouraged, and in response to the IPCC report, there's a bipartisan bill in the House called the Energy Innovation and Carbon Dividend Bill. And it's headed by Deutsch, who's from Florida and knows exactly what's happening to his state. But this bill would put a graduated price on carbon and is projected to make serious inroads in our use of CO2, and actually to respond and bring it down very remarkably by 2030. It just needs a lot of support, and I believe there's a bipartisan bill coming in the Senate too. Do you know about these bills?
Yeah, I know about the CCL legislation so you guys know about Citizens Climate Lobby. So I'm not particularly familiar with this exact bill.
House Bill 7170.
Okay, so economists, virtually unanimous. Economists are just about as sure that raising prices causes people to use less as physicists are that adding heat to things warms them up, right? So economists are virtually unanimous that the way to most painlessly reduce CO2 emissions is by taxing carbon and then returning that money in some form through other parts of the economy, whether it's a dividend check or reduced income taxes or something like that. In the United States, the politics of taxation are complicated. You remember the doctor on the old Star Trek? Damn it, Jim, I'm a scientist, not an economist. And I don't have a position on these bills. I will tell you that I believe economists who tell me that this is the best, cheapest way for us to reduce our carbon footprint. I will also say that I'm persuaded by things I read that it's not the only way. That there are also important roles to be played, for example, by energy targets. For example, my city just passed a resolution to have 100% renewable energy in our electricity supply by 2030. 100% by 2030 is pretty good, right? That's better than Boulder, it's better than California. And that didn't require a carbon tax, that required political will to shut down our power plant and replace it with other sources. So I think there's room for many things. The other thing to remember is that more than 95% of humanity does not live in the United States. Only 5% of the population of the world lives here. So our politics feel very important to us, but you got to remember that virtually everyone on Earth isn't here. And so the solutions to this problem have to include China and India and Africa, not just, California and Colorado.
Well, it also puts a border adjustment on.
Yeah.
So anything coming in that's not paid any carbon tax would have to pay it at the border. Ours would get a benefit, and so it could really.
Virtually every economist also agrees that a single country can't do this by themselves. They have to have this border adjustment, which is essentially tariffs on carbon. Yep.
Can you compare and contrast the sea level rise and fall in Antarctica and Antarctica? My understanding is that in the Arctic, it's ice on water.
Yeah.
So it's like ice cubes
Right.
in glass. It doesn't really add.
So great question.
In Antarctica,
It's all on land.
it's reversed.
Yep. So an accident of geography. The Arctic is ocean surrounded by land, and the Antarctic is land surrounded by oceans, right? This didn't have to be that way, but it is. So both ends are frozen, but at the North Pole, it's frozen ocean, and it's only frozen about as thick as this room in the thickest places. Many places, it's only a couple of feet thick. In the Antarctic, it's ice on land that's accumulated over millions of years, and it's thousands and thousands and thousands of feet thick. If ice on water melts, it doesn't change the sea level. So just like if you put glass of water with some ice cubes in it, and you let the ice cubes melt, the water doesn't spill, right? It adjusts. However, ice on land adds, when it melts, adds to the sea. The biggest ice on land of the northern hemisphere is Greenland. Greenland is a big ice sheet just like Antarctica, but it's much smaller. If the Greenland ice sheet melts, the sea level goes up about 22 feet. 22 feet is a lot. 22 feet is the end of South Florida, Louisiana, New York City, and yeah, lots of places. If the sea level in the South Pole melts, if the ice in the Antarctica melts, the sea level rises not 22 feet, but about 200 feet. It's almost 10 times as much ice in the southern hemisphere as there is in the northern hemisphere. So there's your answer. Of course, it takes a really long time to melt a continent wide of ice. It's not going to happen in our lifetimes.
Chris?
I have a friend who I've been trying to convince that climate change is real, and he's very opposed to it. He seems to be jaded by some claim when he was a kid in the 70s, I think, that
I remember
scientists
this.
were all arguing about global cooling was happening, and that was the big controversy, the big thing happening. So I think he's kind of jaded that that didn't happen. Oh, by the 80s, we're all going to be starving and freezing, and so now he refuses to believe that these new findings about global warming. So what kind of element? Did that ever actually happen? Was anybody ever actually arguing about global cooling?
Yeah. When I was in college, we talked about this, about global cooling. Mostly, there was the discovery of the timing of the ice ages. So eventually, we're going to cool towards another ice age in 100,000 years. Don't hold your breath, right? So it's completely possible that you could have massive amounts of warming in this century and a cooling trend in 100,000 years. They're not really mutually exclusive, these two things. The cooling that we were mostly talking about in the 70s was not slipping into the ice ages, but rather was from air pollution, from particles in the air that reflect some of the sun to space. And we're still talking about that. China has large areas that are substantially cooler than they used to be because of the air pollution in eastern China. The particulate matter in the atmosphere over those cities reflects a lot of sun to space. Particulate matter has a lifetime of like 5 days. CO2 has a lifetime of like 5,000 years. So you can clean up the air and get rid of the cooling effect, which is a regional and local effect. It's not a global effect. But generally, that whole narrative has been massively oversold in a deceptive way. There were, in the 1970s, during that time that your friend is talking about, many, many more scientific articles about global warming from CO2 than there were about global cooling from particulate matter in the air. Some of those particulate matter scientists got the attention or whatever of Newsweek and Time magazine. Remember magazines? But there was the ice is coming or something, cover on Newsweek in, 1976 or something like that. So there's this false story that's being told that, all scientists thought the world was going to freeze by the 1980s, and it didn't happen, and they're all full of it. We've known about global warming from CO2 for 150 years. The story has not substantially changed. The guy won the Nobel Prize for discovering this in 1896. Not 1996, 1896. So your friend has been sold a bill of goods. Yes?
This is on the solution side of the questions. What do you know about the British Columbia company called Carbon Engineering? There's one here also that's called Climeworks, and there's like 7 total in the world that are working on this process of carbon removal, wherein they take the carbon out of the air and do a chemical process that combines hydrogen and oxygen to create fuel. And that fuel, I've read, can be used in any engine that exists today.
So there are more than one technology like that. Overall, we call that carbon removal or carbon sequestration technologies. Remember what I said about the reason why we break carbon bonds and release the CO2 is because it makes energy, right? And so gathering up CO2 from the air and sticking it into fuel molecules actually uses energy. So you have to have energy to be able to do this. You can't, it's not free.
They're talking about combining or like using
Right. So great, absolutely. And remember what I said about if we miss these targets, we have to get incredibly ambitious about sequestering carbon in the latter half of this century. And so technologies like this will be required, even though they're extremely expensive and difficult. It will always be cheaper to use that solar or wind electricity to run your lights and your car and your heat than it will be to use that technology to suck the CO2 out of the air. But we may yet have to suck the CO2 out of the air. It's unfortunate, but it's true. Some of these technologies are much easier than others. By far, the easiest one that we know is to grow biofuel and use the biofuel to make electricity, and then capture the CO2 in the smokestack of the electricity plant, where instead of, you guys know how many, your organization is named after parts per million of CO2. How many parts per million of CO2 are there in the atmosphere?
Right now.
409. Right, very good. Okay, so there's 400 molecules of CO2 in every million molecules of air. In a smokestack above a power plant, it's 200,000 parts per million, 20% CO2, because you've replaced all the oxygen with CO2, if you do it right. It's much easier to suck the CO2 out of 200,000 ppm stack gas than it is out of thin air. So the far easier thing to do is to convert all of our food production into biofuel and starve. And then take that biofuel and use it to make electricity, and then suck the CO2 out of the stack gas and put it in the ground. These other things are experimental. No one has done anything like that at scale. You can do a ton, let's say. You guys, you know a cubic meter of water weighs a ton? Did you know that? A cubic liter of water weighs a metric ton. A cubic kilometer of water, think about that. A cube, a kilometer on a side, filled to the tippy top with water, weighs precisely 1 billion tons. Human beings every year mine 10 times that much carbon out of the ground and set it on fire. 10 billion tons of carbon per year are mined out of the ground and set on fire and turned into 37 billion tons of CO2, because you get the oxygen to account for. A ton is not enough. You've got to capture 37 billion tons a year, year after year after year, and find a place to put it. Somebody did a calculation, I think he was joking, where if you took the entire CO2 production of the United States and captured it at the smokestack and pumped it into the ground, it would raise the level of the ground by 1 centimeter per year. It's probably not true, but it gives you an idea of how big of a volume that is. All right, somebody else. Martin.
I had two things. One is I learned from Chuck Kuchar, once as a researcher at Tufts University, Frank Ackerman, and he did a calculation of the cost-benefit analysis of, or rather put it differently, the cost of doing nothing. And it shouldn't be surprising that fixing stuff after everything broke is a lot more expensive, maybe 10 times more expensive than doing something in the first place, doing it right and preventing those bad outcomes.
I think this is, again, a virtually unanimous conclusion of economists that it is much, much, much cheaper to fix this than it is to wait until it's destroyed our economy and then try to fix it.
Steve wants to chime in there.
Yes. A stitch in time saves none.
Very good.
That is that statement.
That's good.
With
And
the
if I-
wisdom of the ages of women.
Very good.
If I may, my second point, yesterday I heard Jan from Climate Reality Project go through her presentations with the Al Gore slides, and she mentioned something I hadn't known before, and I'm a little worried about it. You mentioned those 409 parts per million due to CO2, but she said, well, if you add the climate factors from methane and other combustibles and gases, you end up more like 485. Or that's the number I remember. Can
It's
you
certainly,
say something?
yeah. So I'm glad you brought that up, Other gases, remember O2 and N2, just 2 molecules? CO2 has 3 molecules, water vapor has 3 molecules. Methane has atoms in its molecule, so carbon, hydrogen, 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 hydrogen. Imagine all of the different ways that molecule can wiggle. So the per molecule absorption spectrum of methane is something like 100 times more powerful than the infrared absorption of CO2. However, currently there's 200 times more CO2 than there is methane, molecule for molecule, in the atmosphere, and the amount of CO2 is projected to go up much, much more than the amount of methane is projected to go up. So although currently the methane may be a fairly substantial part of our greenhouse gas budget, 100 years from now, unless we do all these things that we've been talking about, the CO2 in the atmosphere will increase by maybe a factor of 4, but the amount of methane will not increase by a factor of 4. The other really important thing about methane, and there are other gases too, but methane is the big one. The other really important thing about methane is that it's reactive. Okay, CO2 is not chemically reactive in air. It doesn't burn off and turn into something else. It's already completely oxidized. It's the fully reacted, oxidized state of carbon as a gas. Methane has lots of energy in those bonds that can still be taken out by chemical reaction. So methane actually slowly burns, if you will, in the air into CO2 and water vapor with a time scale of about 10 years. Maybe it's 12. The CO2 is essentially forever, and the methane is a sort of decadal problem. If you fix the methane leaks now, you have a lot less methane in 10 years. If you stop burning CO2 now, you still have the CO2 from last year 1,000 years from now. So the methane, I told this story to Bill Ritter. You guys know who he is? And I did my little methane dance. And he said, I've got it. Methane is the Elvis molecule. It wiggles its hips, but it dies young. So there's one more thing I got to say about methane. Sorry. Methane is the primary ingredient in natural gas. Methane is what you use for stoves in your kitchen. If you burn it, it turns into CO2, and that's good because 200 times less greenhouse as CO2 than it was as methane. If you leak it, it's really bad. So we produce a lot of natural gas in Colorado, particularly with fracking, because people make a lot of money producing natural gas. So methane, because it's got all this carbon and hydrogen bonds, has about twice as much energy in it per unit carbon as coal. Coal is almost pure carbon. You burn natural gas instead of methane, you get half the CO2 for the same amount of energy. Make sure you understand that. Half as much CO2 for the same amount of energy if you burn natural gas instead of coal. So converting our electrical supply from coal to gas over the last 20 years has been very good for our CO2 emissions, made our CO2 emissions go down. However, if you leak 3% of that methane during the entire life cycle, from the time you drill the well, frack the well, produce the well, pipe the methane, get it to your house, burn it in your stove, if 3% of those molecules ever leak into the atmosphere, you have completely undone all the benefit of natural gas over coal. You might as well have burned coal in the first place. It's really bad to leak the methane. Industry thinks they leak about 0.75% of gas, but many independent studies put that number at more like 3 to 5%. So be very wary about claims about natural gas replacing coal as a huge climate solution.
Were you involved in the CSU study that came to those results?
No, but I know those people pretty well. Sorry, I'm talking too much.
No, you're fine. Joel, you had a question. Joel, did you still want to ask a question? No question? Andrew?
So I was just curious, I'm really interested in how we message about this. And I think your presentation sort of represents this. You're talking to a group of very sympathetic people sort of about issues that we're all sympathetic to, and then we talk about climate deniers. How do we talk to and about people who are sympathetic, but who this is their second or third or fourth priority issue? And how do we make this their priority? Like, what is the ask?
It's a great question. So I think in the introduction to the meeting, you said make sure that everybody does something themselves, right? One of the asks is to do something yourself. Now, let me make something clear. If all of us cut our emissions by 90%, it wouldn't be enough, okay? The whole world has to do it, not just the people who feel strongly about this. So you might ask, why should we ride the bus, ride our bikes, turn down the heat, whatever? And I'm persuaded by a group called Alliance for Climate Education. They're called ACE. It's a great acronym. They talk to 500,000 kids in high schools every year. Half a million, yeah, that's it. And they wrap up their presentation with something they call DOT, D-O-T, do one thing. And they try to tell those kids to commit to one action in their own lives and their own families that they're going to do to help solve this. And it isn't because turning off the water when you brush your teeth is going to save the planet. It's because the act of committing to doing something sort of psychologically changes the way you feel about that something.
Yes. Empowerment.
Pardon me? Empowers you, and it commits you, in a sense. Another really, really important thing that I think all of us need to do is talk to one another. Just like we are right now. Yes, I'm preaching to the converted. I understand that. But it's good for you. Doesn't it feel good? Yes. So it helps us. And I do this like twice a month. I talk to people like you, but I also talk to farmers and ranchers, and I talk to conservative churches, and I talked to the Republican Party of Grand Junction. I talked to the Heartland Institute in Chicago with 600 people in one room that all hated me. I think talking to people is one of the most important things we can do. I think this gentleman used the word sin. This is a powerful word. This is a word with tremendous cultural gravitas. And I think there are people for whom that concept for this issue resonates, but there are also an awful lot of people for whom that is a huge turnoff. That I'm blaming you. It's you. You did it. Not you personally. But I try, actually, to stay away from sin. In this talk, you notice I use simple, serious, and solvable. I'm sandwiching the really bad news between a sort of comic relief beginning, there I get your attention and I persuade you not to walk out of the room or fall asleep, and then a sort of call to action, hopeful end, where I try to appeal to your better angels rather than to beat you around the head with guilt. I personally have found, and I've done this hundreds and hundreds of times, that this three-part message works pretty well in reaching people. You know, you guys are easy. You're 350.org. I knew this was going to be an easy night. But you know, I've been in rooms where people are like really unhappy with me, but they still like this slide. They still like to hear that people have the potential to do stuff. People have been through amazing shit over the centuries. I mean, people have faced the bubonic plague and war and famine and death and all this stuff, and we've been resilient and we've come through it. We have to hope in the resilience, in the strength of spirit of human beings to pull together, and almost everyone can resonate with that.
Yeah, that makes sense.
A couple of comments. One is that your presentation is great, and you know, I've been studying this stuff for years, but you've given me language that I can use.
Great.
And I love the 1% and the toilets.
Yeah.
Because that really.
I'm fond of toilets myself.
I love toilets.
Yeah.
That's
Beats the heck out of the alternative.
That's really great. I want to just say that there are some really good things happening, and specifically, you know, you're from Fort Collins, and you guys have said 2030. I'm from Denver. Denver has said 2030.
Awesome.
And last December, Excel said 80% by 2030.
Amazing.
Which is like a huge commitment course, we have to keep them on that.
Yeah.
But what this is it's visualizing how we are going to change
Right.
in concrete ways. And once our electricity supply is really pushed towards renewables,
Right.
we can begin to talk about electrifying
That's right.
our transportation, our home heating, just really making those changes, and that's the kind of thing we can do ourselves in
Here,
our
here.
neighborhoods.
It's, there's sort of two steps. One is clean up electricity, and the second is electrify everything. And that's like a 1-2 punch to solve this problem. It's much harder in the developed world. Ironically, remember, almost everyone doesn't live in the developed world. Almost everyone lives in the poor parts of the world. It's much easier for them to just skip that part that we went through, right? Just like they're not going to build landlines in Africa, right? They're going straight to cell phones. They'll go straight to renewable electricity and then electrify everything. When I was young, I was propagandized, inculcated, whatever, against electric heat, right? Electric heat was bad in the 70s, in the 80s, because it was baseboard heat that sucked down your electricity. You had these huge, horrible bills, and it was very inefficient. You wanted to have the combustion happen in the home, in a furnace, because it's much more efficient than running electricity through the wires. Well, that's very old thinking now. We built, remodeled a 1924 house, and we put an air source heat pump that is essentially air conditioning running backwards, and it's very comfortable in January in Fort Collins with electric heat that comes out of this heat pump, and then we got solar panels that produce the electricity. It's awesome. So everybody has to forget everything you ever learned about electric heat being bad. Electric cars, electric heat, electric hot water, electric everything, once you've cleaned up electricity. Yeah.
I just want to say, we can't have people wait until the grid is clean. They have to start it now because the time
Yeah, it takes
is
time.
very short. And I, like you, have taken an old house and I have converted to electric heat, electric car, and that works on an old house at 6,000 foot elevation in Northern Colorado.
Isn't that something?
But we need to do it, and it comes down to, the toilet is obvious because people smell the consequences of not having a flush toilet.
Yeah.
CO2 is not an aromatic
Yeah.
with the same term.
That's right.
And so we need to have a cultural change.
Yeah.
It's culture. It's really culture, which is why I mentioned the word sin with you.
Well, it's all right.
But the cultural change has to happen, and people in their own lives, you can't depend on government. We've seen what we can get for government. But everybody has to do it in their own lives, convert everything to electric, and the grid will come. But if you do PV,
If you wait too long, yeah.
yeah, but you don't, then you do PV and you're good.
Okay.
One more question, Maggie.
How often when you do these presentations, do people talk about parts per million of carbon, and as it goes up, that, like, for instance, when you hit 1,000 parts per million, there is cognitive decline in
Yeah.
human beings?
That is true at very high levels of CO2, but it has to be really high before you really start getting badly cognitively impaired. For example, in this room, it's probably 2,000 ppm right now. Yeah, I'm all right, kind of still hanging in. The typical, maybe not this room, but most indoor air quality monitoring kicks on at something like 1,000 or 2,000 ppm, where it's not that the CO2 is bad for you so much as that it's an indication of stale air and it's very cheap to measure. So the ventilation system in a room will trigger and start mixing the air when it hits, say, 2,000 ppm. So people put up with 2,000 ppm all the time. Think about it like this. The air is 20% oxygen. If I breathe in 20% oxygen and I hold my breath for a really long time, it'll be 20% CO2. Okay, 20% CO2 is 200,000 ppm. I'm blowing out 100,000 ppm CO2 all the time. Doesn't kill me. It's not toxic. It's just not oxygen. So it interferes with your pH of your blood and some other stuff. But the physiological, if we wait to fix this till it makes you sick, we are really fucked. I'm sorry, I shouldn't use that word in church.
Harvard studies showed that at 1500, you actually did get cognitive impairment that affected grades for students taking tests.
Yeah, I believe it. Stale air.
I would like to wrap up because we're very much over time.
Sorry.
Thank you. No, it's fantastic,
All right.
and there's so many questions.
And all my slides, everybody can have them. Simpleserioussolvable.org. You can download the slides for free.